Hello everyone, my name is Le Tianchen. Today I'll present our paper towards sample-efficient apprenticeship learning from suboptimal demonstration. This work is done in co-robotics lab with my co-author Rohan Pleja and my advisor Matthew Gamble. Robots have been applied to every aspect of our life. However, traditional design for task controllers requires an army of robotic experts for each task, greatly limiting the possibility for realizing ubiquitous robots. In contrast, learning from demonstration techniques enable robots to learn by observing a human demonstrator's performance of the desired skill, empowering end users to program robots to achieve their personalized goals. However, human end users may not be able to provide ideal demonstrations for the robot due to diverse heuristics. Our previous algorithm SSRR works to learn from suboptimal demonstration. Let me explain first what noise performance relationship is as a background for SSRR. Here is an optimal policy on half cheetah. If we inject noise into the policy, the performance will drop. And with more and more noise injected, the performance becomes worse and worse. But how does the performance degrade with varying noise levels? If we plot the corresponding noise performance data points, we could obtain a noise performance relationship. SSRR shows that noise performance relationships are not homogeneous across environments and policies. To correctly capture this relationship, SSRR generates noisy trajectories and utilizes a sigmoid function to fit the noise performance relationship. It could then infer the idealized reward function and optimize a policy with a learned reward to achieve better than demonstration performance. In S3R, we address the issues presented in the noise injection process. For instance, noises might cause safety concerns and has randomness in its degradation effect. Besides, noise injection may not be able to accurately represent the whole scope of suboptimality. For instance, if the objective is to make a robot cheetah move forward, a random policy is likely not able to move. However, a policy moving backward yields even lower reward. Those thoughts motivate us to propose three alternative approaches for noise injection. We could reduce the number of demonstrations available to ARL, or reduce model capacity with ARL, which means that we reduce the number of layers in the neural network. A third way is to increase network weight sparsity by enforcing L1 regularizations. By substituting phase 1 of SSRR, which is self-supervised data generation, we have S3RR. To evaluate S3RR, we compute the correlation between the learned reward functions with the ground truth reward function. We could observe S3RR is able to achieve near perfect learning of the idealized reward in half cheetah. We further optimize policy and show S3RR could outperform the suboptimal demonstration in SSRR on half cheetah, but performs worse on ant. In general, there's likely no one degradation method that fits all domains, so we could run both S3RR and SSRR and pick a better resulting policy across the variations. In conclusion, we develop S3RR, a framework to learn from suboptimal demonstrations. We illustrate it continues the success of SSRR, and more importantly, it opens the possibility to discover effective degradation process for broader domains to achieve learning from suboptimal demonstration. Finally, I want to thank sponsors for this work: MIT Lincoln Laboratory, Office of Naval Research, NASA, and Kanoka Minolta. Thank you for your time, and we look forward to seeing you in the discussion session.